Okay, hello everyone. I'm going to start the session. My name is Yaron. I'm a co-founder and CTO for Iguazio. I'm also blogging and presenting a lot in the areas of MLOps. What I'm going to cover today is the aspects of operationalizing machine learning and going beyond the training. A lot of people think that MLOps is about automating the training loop or experiment tracking. We're going to see how MLOps allows us to build applications that consist of machine learning and data processing and so on. And I'm also going to show some demos, but before we're diving into the session, let's start with the problem and see what kind of challenges we're trying to solve. Most people that go into machine learning and AI projects, or especially within the data science team, they look at the world in this perspective, just like the slide you see here. The data somehow magically arrives into some store. They take the data, they run some data preparation, they train it using their own code or built-in or managed services for AutoML or training. And they evaluate the model, they see that it actually works. When they finish, they generate a model object or model artifact or model container, and that container is used by other teams. And this is sort of an interactive flow. The data somehow arrive here, although in reality the data just doesn't just arrive. It has to come from real sources, and the model, someone else is taking care of how this model is getting deployed and integrated with the business application. The challenge is that in reality the world looks more like this. You don't just train a model using Jupyter and that's it. You have to train the model sometimes and retrain the model using live data sets. Sometimes you need to do the training at scale with hyperparameters. And when you finish the training, you need to make sure that you're logging all the different information about the training, data lineage, results, comparisons, and also register whatever you're generating, whether it's a model or different layers or data assets and so on. All those things needs to log into a way that could be consumed in the production environment. So if you're logging just a model file, somehow you need to wrap it with metadata, you need to store it in a central location, you need to be able to search and load it, and so on. So this is just the training part. But beyond the training part, there's a full life cycle of managing and generating the data, usually done by different teams of data engineering and data management. This is where you bring the data into the training environment by essentially analyzing it using tools like Spark or Pandas or Flink and so on. And this data is not only generated for the training, the same data is required also for serving a model. So let's assume I'm predicting some fraud. I need to ingest data about credit card transactions and use it for training, but on the same time, same data is used to understand what this customer did, historical transactions, and be able to serve or score based on all that information. So this data that's being generated for the training environment also needs an aspect of real-time stream processing or data generation that is used for serving. And the serving usually is not just serving a model. A model is something that gets a set of numbers and runs some equation and spits out a new set of numbers. But in reality, the data arrives in different formats. For example, you may have a JSON structure with the user ID and some other data. This data needs to be enriched, contextualized with other user data or with product data or environmental data. Maybe you need to run various validations on it, do the scoring. When you do the scoring, you need to push an event, update some databases. So there's a complete pipeline in the production, which involves far more than serving a single model. Sometimes even the model serving part itself consists of an ensemble of multiple models that needs to be served together. And last but not least, there's all the aspects of observability and monitoring. So you need to collect data from data processing, from the training, from the serving, and be able to do things like analyze drift or accuracy or measure business SLA and other metrics potentially that you need to do beyond operational metrics, CPU, memory usage, failures, errors, and so on. So, and the challenge about this is that many organizations, when they move from the interactive data science model development into something like that, there's a complete refactoring and re-engineering effort, because you can't just take a notebook and make it scalable, run over containers. Someone needs to do all this ML engineering work. Someone else needs to do all the data engineering work. You have DevOps involved, data management, and so on. And this is really where organization gets stuck, because they need to suddenly do a lot more engineering, sometimes a magnitude more engineering in pushing a real machine learning application to production. So what we did in Iguazio as part of open source initiatives, and also promoting it in the industry, is a different philosophy. Instead of thinking about research and then re-engineering everything you're doing into production environments, let's think, what do we need in production environments, and then make sure that whatever we're building doesn't need to be re-engineered. It essentially fits into the production environment with a seamless work as possible, with minimal work and more automation. So the general idea is that if you're breaking the previous diagram, you see that there are 4 different segments that you need to address in order to build those machine learning applications. The first segment is building features. So essentially tapping into operational data sources, whether it's data in S3, object store, or whether it's real-time data arriving from Kafka, data from warehouses, Snowflake, BigQuery, etc. Video feeds. All those things need to be processed, prepared, and generate features that are already meaningful. Including aggregates and encodings and other things that will be usable for the next phases in the pipeline. The next phase is to essentially be able to trigger training or model preparation pipelines automatically every time you generate new data, every time you change code, and also build those automated pipeline in a way that you're not just training the model. Maybe you need to train at scale. Maybe you need to do evaluation and testing. Maybe there's a portion of data preparation. So you need something like a CI/CD pipeline for your machine learning work, and we'll see how we're achieving that. Once we've built a model and we've built data assets in the feature store that are used for the real-time serving and application, we want to build those real-time pipelines and include multiple steps. Again, data preparation, scoring, validations, actions, metering, and so on. So we use a technology for building real-time pipelines. It's a serverless technology. We're going to see that in a second. And finally, we want to monitor and meter all those different things that arrive from the serving, from the training, be able to automatically detect drift, anomalies, be able to report on different business metrics, and feedback everything into the feature store so we can just retrain. Every time we want to retrain, we don't have to go through a huge ritual. We can just click a button and retrain based on production data, or allow data scientists to peek into the production data and be able to explain results, retune their models, and so on. So this is what we call production first mindset, and it's all glueless. There's no, unlike the previous example where there's a lot of glue logic that someone needs to build, here, because in MLRun, which is an open source project, everything uses the same schema, the same metadata. All those different things are glueless. And the general idea is that it interacts with almost everything. It interacts with any external notebook, and I'm going to show you how it interacts with built-in, training or AutoML services at the cloud. It works with most of the CI/CD frameworks, Jenkins, GitHub Actions, GitLab CI, and so on. And again, many other tools. So you just integrate through a very simple API, and you automate your entire path to production. What are those things that we need to automate when we're moving into production? So think of a data scientist. He builds a simple code, Python, that takes some piece of data, runs some pandas, and generate a result, or another piece of code that takes some piece of data, creates a model, tries to fit, and save the model result. All those pieces of data, when you're working in a standalone in a Jupyter or in your PyCharm, it's nice, and you can put breakpoints and debug, but it's not production worthy. In order to turn something into production ready, you have to be able to first package it, put it in containers with all the different sources and source packages, You need to be able to run automated testing, unit testing, and system testing. In many cases, you're processing lots of data, so you need a mechanism to scale out your workload across multiple virtual machines or containers, or maybe scale out your data and partition your data, or scale out the different parameters that you're going to examine with your training by doing distributed hyperparameter search, and so on. Also, in many cases, when you're developing, you're not thinking of performance. But when you're moving into production, if you haven't written the code efficiently enough, either you're going to pay a lot for additional resources in the cloud, or you're just not going to meet the SLA. You're building a scoring engine, needs to respond to a user request within several milliseconds, but it may take hundreds of milliseconds because instead of doing something in cache or using a key value query, you're using a SQL SQL scanning transaction or something like that. So you need to be able to build everything in a way that is very cost effective, very high performance, that meets the application SLA. And there are many other production aspects like instrumentation. Everything needs to be monitored, logged, versioned, secured, access control across all the different data assets and code assets. And everything that you build has to be automated. So in order to avoid manual processes, you want to build sort of skeleton, a workflow, and trigger that workflow automatically every time you need to do rolling upgrades, every time you need to retrain a model, and so on. So these are all those things that you need to do, which are usually engineering tasks, ML engineering tasks, data engineering tasks, and those are the things that take the most amount of time. This is like 10 times more work than just training your model. So the traditional way of organization is building the development, in your IDE, whether it's PyCharm or Jupyter or something else. Then giving it to some ML engineer. This ML engineer essentially takes the code, refactors it in order to make it ready for containers and packages, maybe potentially scale across TensorFlow or other frameworks. And once you have those components, someone else needs to compose a pipeline, essentially the data engineering piece, the training piece, the evaluation piece, creating the serving flow, and so on. And after all of that is done, you need to think about how do you monitor the different metrics and how do you take back the results from the monitor and use it in order to retrain your model or recalibrate your code. So this is a very tedious, very engineering-intensive work. So what we've looked into is how to automate this entire flow using a baseline of serverless technologies. So instead of doing everything manually, you code your functions in your native environment. I'm going to show you like just building something in Colab, and in one click, essentially turning it into a fully managed, elastic, auto-scaling service that can handle almost any scale with built-in telemetry and monitoring and security and all of that. And then when you want to build something more complex or consists of multiple stages of data processing and training and serving and so on, you just compose it using those individual building blocks that plug into a complete environment. And because all the monitoring is built into those serverless engines, you don't need to do any coding for monitoring. You're going to get automatically model drift detection and anomaly detections and resource monitoring and profiling for your code and lots of other services without writing a single line of code. And this allows you to essentially go back and redeploy models after retraining or examining the production data and recalibrating your models without a lot of work. And this is based on a lot of testimonials of people using that technology. Sometimes it's even 12 times faster time to market because they don't have all this huge engineering effort that you have in the traditional processes. In MLRun, which again is an open source project, go to GitHub MLRun or mlrun.org. The core concept is about serverless function. What does it mean? When we're running all those different jobs, whether these are training jobs or serving jobs, since we're getting lots of data in, we're getting input like parameters, credentials, data assets, tables, streams, etc. Maybe some labels and tags that we want to tag our jobs with. And then we need to run the code. Instead of running the code, again, in a local environment, we may want to run the code on top of a distributed job over Kubernetes. So we need a way to package our code distributed that, convert it automatically to microservices, be able to auto-scale it using different technologies, and track all the results and record the different results. Results, again, could be matrix, numeric values, operational data like logs, CPU, memory, GPU matrix, data assets, and so on. So we can build those building blocks where essentially you're writing a code, you're specifying what you need, and this gets deployed automatically. And all those different assets are sitting in a sort of a metadata database that could allow you to track them and visualize them, but also connect those different building blocks to build more advanced pipelines. So what some of the challenges that people have when they're writing code in the usual way is that you have to add a lot of code for telemetry, for monitoring, for getting variables in and out. Sorry for that. Integrate with CI frameworks, or there's again all the integration around Git and reporting systems. When you want to distribute your workload, again, there's tons of work in distributing the workload and putting data, for example, in a shared repository, building for every framework. There's a different way of distributing your workloads. Again, there's lots of different tasks that you need to do. So we want to also automate all of those tasks. So the general idea with those serverless functions that you're using across your system is that we want to essentially write a very simple code and add automatically all those different operational engineering tasks automatically without doing anything special. So this is an example for just writing a training function, just regular training function. There's a special concept around data movement. So instead of working with URLs or something like that, you're working with data objects. This allows you to essentially work with data that could be in an object store, in a file, in a database, and so on. You don't need to think about how it's actually being materialized. And then just put in some parameters in your code, run your training job. You need to add one line of code in your job in this case, and this one line of code essentially hides all the ML engineering tasks and all the MLOps tasks behind it. So it's essentially going to log all your artifacts and versioning them. It's going to log your models. It's going to analyze the lineage of your data. It's going to be able to scale out your model training. It's going to do checkpointing. It's going to export the data to various systems, whether these are Git systems or TensorBoard, etc. And so there are so many things that are essentially being built automatically by just adding a single line of code. So the general idea is that I can build this piece of code in Python and use a single call to turn this Python code into a fully managed service over Kubernetes or a managed service. I'm just taking my code, converting it into an MLRun function, serverless function, and then I could just go and execute that. I can execute it with parameters, or I can execute it with hyperparameters. If it executed with hyperparameters, it's actually going to distribute the job potentially across multiple containers and do all the analysis of which job is sort of going to generate the best results. So this is the general idea. And again, it's automatically collecting lots of matrix and data and packaging your models, all that automatically. And we're going to see a demo shortly. So with that, let me open. Sorry. So I'm going to take Colab, which is the Google Collaboratory. I'm actually doing it on purpose just to show you that you can do it from any environment that you want to run this. It could be in your PyCharm, in your managed Jupyter, in your Azure ML, SageMaker, Colab, etc. So the only thing I need to do here is install MLRun, which again is this service, this package for automating all your work. Because I'm working against a remote Kubernetes cluster, I need to put some credentials. I'm not going to show you my credentials. And this essentially logs remotely into a Kubernetes cluster with all the different services and the MLRun user interface, which we're going to explore in a second. Next thing I need to do is create a project. A project allows me to later on work in CI systems or Git systems, because I can just save a complete project, load it on a different cluster, run it. And there are many automation features around this sort of project concept. And then I'm writing a piece of code. This code is doing a simple data generation. I'm just writing a simple function. This function can use something called a context. It's optional. And with this context, you can choose to log in information. You can grab secret credentials from the context. You can do different things with that context. So I can build a function that generates data and then logs the data set result. I don't need to care about how to save this data, whether it's on S3 or a file. Everything is configured automatically. So I'm just going to generate this function. I'm writing it locally. In order to record that function in my project, I'm just one line, and I can also specify like the container image, base container image used for deployment. Again, it knows how to automatically build packages and all of that for you. I'm going to show that. The next thing, I'm just going to execute my function. I can execute my function locally because I want to do debugging and all of that. And this is the result. If I'm going to click on the URL, essentially I can see the progress of my job in the MLRun user interface. Remember, we're connected remotely to a cluster with MLRun. So I can see the inputs to every job. I can see the artifacts that were generated by the jobs. I can see the logs, the numeric results, and so on. This is sort of a boring job, but again, I can see all the different details that get recorded. This job that I ran is an API endpoint that I could just query. I can see what's the status of this job. Maybe it's running for half an hour. I can see if it's completed, what were the output of that job. I can even visualize the outputs, although they're stored in like an object store somewhere. I can just go and call those results back into my system and visualize, my data frame and so on. Now let's assume I want to do training. So in MLRun, one of the nice things is you have a marketplace. You don't even need to write functions. You have like AutoML function and data preparation function. So you can just go and import a training function and then execute the training function with different parameters. If you really want to see the different parameters, you can just document, just do function.doc. If you want to see that in the marketplace, you can just go and see the user examples of every function in the marketplace. And I could just go and execute that function. In this case, just giving it which class I'm going to use for training and maybe some parameters. And this will automatically go and take the data, because the input of this function is the output of my data generation. So I can essentially take the one function, execute it, generates an output of a data set. I can run training, essentially just saying, use the data set from the previous step and just go and run training. When I'm running this training, again, it does a lot of things. All this auto-tracking, auto-monitoring is done automatically. And I could see that the function generated different outputs, accuracy, and F1 score, and also it generated many different artifacts. Artifacts could be visual artifacts like feature importances or a confusion matrix or ROC curves, etc. Could be data sets, could be many different types of artifacts. Again, if I go into the UI, I can see all those different artifacts visualized, and I could see the different results. If it's a hyperparameter job, I'm going to see sort of result comparisons and all of that. And again, every job is versioned. I can see the different instances of the runs, so I can go and compare different runs and see which one is better and why and so on. And all of that is done automatically for me. So again, I did the training, I generated the model. And the next thing I want to do is serve the model that I just created. So in this case, I need a new function. This is a serving function this time. So I'm creating a serving function. And this serving function object, I'm just going to add a model to it. The model is, where am I going to take the model? I'm just taking the output of my training function as an input to my serving function. And saying, this is an sklearn class model, just build a topology. Here we're building a very, very simple topology of, data is coming in, going through routing, and being served using a model. But you can build very complex pipelines. You can see the MLRun documentation, including NLP, like taking a PDF, breaking it to paragraphs, running first NLP model, then running classification models, and so on, or doing feature engineering or data validation and then running a model. But again, here we're just using the simple case. I'm importing a serving function, I'm adding the model to it. In order to test that, I don't want to create a container. Again, I want to be able to debug and see things quickly, so I can create a simulator, a mock server for my serving function. So this is what I'm doing here. I'm creating a simulator for my serving pipeline. I'm pushing some data into it, a request, for example, to list the models, and it's going to show me that I have only a single model. I can test it with some sample data set, just to infer and see the result of the classification. And let's assume everything is good and I'm ready to go. The next thing I want to do is just do deploy. I can just go and say deploy function. This will automatically convert my code into a real-time serving function. It runs as a service on that Kubernetes cluster. You can see the different stages of building the containers, deploying the APIs for the serverless functions, and so on. And then I'm just going to get an endpoint, a real URL endpoint that I can just go and invoke, again, a request against it and see the response coming back from the real function. So you can see that I haven't done any engineering task, any DevOps task, any MLOps task. I just took my code, I ran it, it ran, the first case ran locally, and then I took the result of the first thing and pushed it into the training function and ran it. By the way, you can see that the training function, I didn't turn in the local flag, so you can actually see that it created pods, created containers on Kubernetes and ran those things. So I have a very simple local environment experience, but essentially I'm running over a big cluster that I can schedule job along with anyone else in my team. I can save a lot of money because all that is shared infrastructure that we're all going to use. If I want to have GPUs or some other resources, I'm just dialing up a flag here or there, and I can just run across a lot more resources. And everything, again, as you've seen, is monitored and metered in the system, including the models that I just generated. I can just go into this project, and I could see that I have a serving function, which is actually running. I can even see the code in the serving function. If I want, I can see the models. I can monitor. We'll see that in the next example. We can monitor the models. We can monitor the accuracy of the models, again, without writing a single line of code. So this is the first example, which is relatively simple. Let's go back into the presentation. So this is, again, very simple. I'm building some data engineering code. I'm training some models, distributed or not distributed, and I'm serving a function. And you could see how you could do it very easily and move things to production. But in reality, production is not just getting data from a generator function or from a CSV file. Data arrives from real production environments, from operational databases, data warehouses, streaming, etc. So we need a way to automatically generate the data for training and serving. And this is done using a feature store. And MLRun has one of the best feature store built into it. The next thing we discussed is building serving pipelines, not just a serving endpoint, but being able to do data preparation and data validations and serving models and so on. So we need a serving pipeline. We also need to be able to monitor and retrain the models, because we're not going to train manually every time again and again. We want to retrain models every time we change data, every time, maybe every few days, when we change the code. And we want to make everything work as part of a continuous deployment pipeline. We don't want to do things manually. We want everything to be automated and integrated with the traditional CI/CD systems that we're using in the organization. So these are 4 key components in MLRun that we're going to see in a second, also in a demo. The first one is the feature store. The feature store is not just cataloging. A lot of things people confuse feature store with a way to catalog features. One of the most powerful features of a feature store is the ability to generate features automatically and essentially store them in different views for real-time and training. So it eliminates all the data engineering work and all building stream processing and all this sort of very advanced work by just composing a set of transformations and deploying a feature set, as we call it. And this feature set essentially builds your analytic pipeline and knows how to generate the features for your model serving, for your training, for your drift analysis, and so on. So the way that the feature store works, the first has connectivity to different data sources. MLRun supports different, everything from object store and Snowflake and MongoDB and BigQuery and many other different data sources without doing any work, just specifying a source, and also many real-time sources, by the way, Kafka, Kinesis, HTTP, and so on. The second thing that it does is essentially it builds a transformation pipeline for converting the raw data that arrives, building things like joins and aggregates and groupings and decodings, etc. Once the results are ready, it's being cataloged, and from the catalog, you can serve it into those different applications. We're going to see that in a second. When you're doing training, for example, it knows how to create new snapshots of the data, because if you're doing retraining every week, you need to make sure that you're creating a snapshot of the last week data and doing training just on that, and also versioning everything and logging it and so on. So all of that is automatically built using the feature store. So again, as I mentioned, you can just build a transformation pipeline using the SDK. You can choose material views like real-time, offline, time series, and so on. And it's not limited to machine learning data. It's not limited to numeric data. There are many examples of people that build using that technologies, NLP pipelines or video stream processing pipelines, and so on. So feeding data on one end, building a set of transformations. You can see here examples of different transformations for different applications, and maybe even composite applications where you feed in some, in this case, a PDF example that has a combination of text and images and numeric data, and essentially processing all of that at once. So this is the first component of the feature store. The second component, and they're all essentially using the same underlying technology of serverless functions, is the graph, serving graph technology. So assuming you want to build an application, you don't just serve a model, again, take numeric data and respond with numeric data. You have to fit your model into a live application environment. So let's assume you have an API and you have some JSON message and you need to parse it and maybe extract the user ID from that JSON message and enrich it from data from the feature store, maybe do some additional pre-processing, and instead of serving one model, maybe you want to serve an ensemble of models and choose the average result, and potentially some post-processing, take the result, push it to a message queue or to a database. And so instead of building it using different teams, and every time you need to version or deploy, you need to coordinate across everyone, you can just build it as a simple graph of operations. Many operations are built-in operations provided by the libraries, for model serving, for data processing, and so on. And you can also build any custom logic that you want. So in order to build those graphs, you just build, the topology of the graph based on, again, built-in classes or your custom classes. We've seen a second ago how I can build a simulator and just go in and play with that simulator and test my code and put breakpoints and tune it. And once it's ready, the only thing I need to do is deploy. And I can even generate it in one place and deploy it on a different place where I'm not confined to doing everything on the same cluster. So this is the second key technology in MLRun, is the ability to build all those complex real-time pipelines using a very modular and simple strategy. And the last, almost the last aspect is the model monitoring, and we're going to see that in a second again. So all those different classes, they automatically collect telemetry about everything, and this could be viewed, and we can analyze automatically what's drifting and not, who's using what resources, where do we have issues, error, failures, etc. All of that is monitored automatically. And the last piece where people I see are most interested in is how to automate the entire flow. So let's assume I'm building a pipeline, and my pipeline comprises of those 4 steps. The first one is training my model. After I'm training my model or multiple models, I want to run different validations on it. In some cases, you want to run optimizations on the model. For example, in deep learning models, you can convert it to ONNX compressed models, which makes it much faster and more efficient. And after you've done this optimization, you can deploy the model into a production pipeline. And not only that you want to do this pipeline interactively or during development, you also want to be able to trigger that pipeline automatically in various events. For example, an event could be someone changed the code and pushed the commit into a CI system or to a Git system. A change could be that someone created a new data set and wants to retrain based on that new data set. So you want to build those automated pipelines. In MLRun, the general idea is that you build functions, and then you just wire up those functions and you build pipelines. And those functions could be scheduled, could be triggered, and it has very good integration with Git and CI systems like GitLab, GitHub, Jenkins, Kubeflow, and so on. So we're not trying to reinvent the wheel until you go use our CI system. We're essentially going to plug into existing CI systems and be able to get triggers from the CI systems, get code from the CI systems, and then push back results, like you can see here, essentially as commit results back into the CI system. So again, if you have an organization that already developed practices for continuous software development, it's just going to extend them into machine learning aspects of being able to compare results and be able to track data lineage, being able to do a lot of reporting that doesn't come out of the box in traditional CI systems. And again, you can also use the marketplace to use built-in functions for the different integrations. So that's in general. And as I mentioned before, this is an open system, so you don't have to work with tools or user interface that are provided by MLRun. There are many plugins to essentially all the results of MLRun could be viewed in TensorBoard as well if you turn it on. You can view everything in the different CI systems. You can export information into Slack or other channels. You have widgets and plugins to Jupyter, so you can actually visualize all this information in Jupyter. So this is in general. And when you're thinking about how to really automate this entire flow of development and moving to production and staging and so on, this is an example I created based on some work with different customers. This is how they're using. Again, you can have different approach. Everyone has different philosophies on that. But in general, we separated to 3 different stages. The first stage is development. Someone works on his laptop or on a development cluster, and he commits, he creates a branch of the overall code. Again, we organize things by project usually, like a business problem will be a project, and this project may have some ways of gaining data or generating data or processing data, may have some aspects of training, some aspects of the production or the different pipelines. So all of that sits in a Git repository, configuration and code. And you just go, you create a branch, you work on this branch, and you do interactive testing, as we've seen before, just going, running something, seeing the results. In many cases, attaching it to a small data set. We're not going to run across a terabyte of data, maybe a few megs of data just to see that things work well. When we finish that work, we're essentially committing our work back into the development branch. Someone needs to go and approve that. So first, usually in CI systems, you're running different static tests, like Black and Flake 8 and other custom engines. The next thing that we want to run is build a pipeline, but this time, instead of running the pipeline in an interactive fashion, we want to get it triggered from the CI system, and we want to use larger data sets, because now we can just wait for an hour and let it work. We are not doing interactive work. And we want to generate reports back into the CI system. And someone sees all those results in the CI systems or of different tests and will approve and merge that work. This will go into the development branch. In some cases, you'll have additional tasks that run periodically, maybe on a daily basis or every few days, to run further regression on your code. At a certain point, you want to create a new release of your product. Again, your product could consist of training pipelines, serving pipelines, application integrations, data preparation, and so on. Portions of that or the entire thing. So when we're merging code into production, the first thing that we want to do is business validation or canary deployments, essentially trying out our code on sort of a test cluster, sometimes maybe even using production data to validate it actually works. If it works, approving this, tagging, creating a release, and rolling upgrade into production. So this is the way we're building the full automation. And the nice thing about it is nothing changes across those different steps. You don't need to recode. You just need to go run something, test, fix, and move to the next phase. There's no re-engineering step whatsoever. And you can build complex pipelines, not just thinking about the model serving. This is an example that one of the demos you can see it in the link here of a full fraud prediction application. So on one end, it uses the feature store to build features from different data sets, live data sets of real-time transaction feeds and different account activities. So it's building features. Those features can later on be explored using data science tools, pandas or Spark. Then automatically, when we want to run training, we generate a snapshot from the feature store. We run feature optimizations, AutoML to create the training model, and deploying the production pipeline. When we deploy the production pipeline, it essentially creates those real-time Nucleo functions that serve the models, run the operational pipeline, the data enrichment, and so on, and work against the real-time features. Those functions generate a lot of telemetry, which is collected by the model monitoring and written back into the feature store. So then if we want to do retraining, the production data could be used in our retraining logic. So this is the general idea. Let me move into second demo. This time I'll use Jupyter, regular Jupyter, connected again to the same service. I see a lot of questions. I'll try and get to all those questions just right after the demo. So there is another demo. All the demos, by the way, are in MLRun/demos. You have many different demos. There are also a lot of demos built into the MLRun documentation on the different sections. There's lots of documentation and examples. By the way, in order to install MLRun, you don't even need to have a Kubernetes cluster. If you just want to run it locally, there are instructions for running it on Docker, Compose, essentially one line, setting an environment variable, running it with a single line, and then just opening the tutorials and running them. So you don't have to use a Kubernetes cluster. Again, obviously, if you want to scale, you want elastic computation, you do need to go for the larger installation instructions, or you can use the Iguazio managed service without installing, or just do an eval of the system. So going back to here, let's talk about the feature store and building automated feature engineering. So let's take an example. In this case, it's a network operations predictive maintenance demo. So let's assume we have sensor data arriving from different machines. We have metadata of the different machines, machine ID and manufacturer and model, etc. This is static data. But we also have live data of actual vibration and temperature, or CPU and memory matrix, etc., that feeds all the time into the system. So what we need to do is first create a project, as we discussed before. Part of that project, we can put different things. We can add parameters to the project, create some functions. This is actually using live streams, so it has also streaming data configured here. And then the next thing that I'm doing as a data scientist, I'm building features. I don't need to understand anything about stream processing, etc. I'm building logical pipelines of features. So the first feature that I'm building is a static feature table feature, essentially the device tables. So in order, my graph, computation graph for the device table is essentially just doing one-hot encoding, say feeding the data of the device table, doing one-hot encoding on that, and generating a new data set which is encoded. Again, one line of code for the transformations. I can plot it. I can visualize the result of my data engineering pipeline. You see I have one-hot encoding built for me automatically, and that's it. Now, obviously, anyone can do it with pandas with one line of code. The real beauty about the feature store is that I can deploy that on Kafka, on a streaming engine, to do real-time work or scheduled work across terabytes of data with one line of code, essentially saying, take this thing, deploy it. We're going to see that in a second. But as a data scientist, I can just go develop, train, test, and see how it works. There's another slightly more advanced pipeline for the time series matrix. Here, in addition to things like encodings, I may want to do aggregations. I want to take the different matrix and calculate average, standard deviation, build time series windows. So I just need to define that this is the pipeline that I want to create. I can again go and preview, feed in some reference data into my feature store engine and see that again, you see all those aggregates were built automatically for me, and I can save it. I have a third data set of labeled data, essentially telling me that there's an error on a device. It needs to be time shifted, it needs to have aggregates. So I'm not going to dive deeper, but again, I'm building a third pipeline. So we have three pipelines. One is feeding labels, one is feeding time series matrix, one is sort of static data. As a data scientist, I can just go and ingest data from a reference file or a reference data frame because I want to run training. If I want to deploy that now in production on real-time streams with Kafka and so on, I just choose a different method. I just say, take that feature set that I created and deploy an ingestion service with that feature set and a source, which is like a Kafka stream. That's it. This is automatically building microservices, connecting them to a streaming engine, doing all that in real time, writing the results to offline data set in Parquet, real-time data stored in a key value. All of that is automated, single line of code. Think about it, it's like 3 months of engineering if you do it the usual way. So this is building the data and generating the data for either interactive development, the first method I showed, or production environment with streaming data. Now let's assume I want to train a model based on that data. So I need to build a feature vector that will use all those different data sets. I need the device matrix, I need the static data, and I need the label data in order to train my model. So this is where you create something called a feature vector. So essentially, it's a composition of different features from different data sets. It knows how to stitch time automatically. It has something called the time traveling. So it will know automatically how to build data set in a correct fashion. I'm building that feature vector. The next thing I'm saying, you know what, give me that feature vector and I want to visualize it or use it as a data frame. So you see it joined the data from the metadata, from the time series, the labeled data, all of that is joined together as a data set for training. And then I can just feed that into a pipeline. So I have a pre-baked pipeline already set up here. Remember those run functions that I used before? I can just chain them as a flow. I can say, first get the offline features. The next thing I want you to do is run classification. The third thing I want you to deploy the model serving. Maybe I want to run some additional testing. And so I can just describe a flow. And this flow can either run locally as a process, could also run over Kubeflow or other CI system. You just choose which engine runs your workflow. So essentially, I'm just running a workflow, providing it some arguments, the feature vector, the target model name. I can also create a time window for building the feature vector. Again, if I'm retraining, I may want to use retraining for the last 7 days, not across the entire data set. And when I'm running it, I'm essentially going to just go and see the progress of the pipeline. Although it's running on Kubeflow as an engine, you can actually visualize it from your front end or from MLRun UI. We're going to see that in a second, and generate the results. when it's ready, I can just go and invoke the serving functions that were created as a result of that pipeline. Okay, and so let's go. So this is this network operation demo. So you see I have a bunch of functions here. I also have the serving functions. There's another function which is auto-generated, is essentially the model monitoring function. If we go into the feature store, we're going to see those. There's actually 4 feature sets. You see the fourth one is the results from the production, from the serving. And we could just go into each one of those features, see the metadata. All that is automatically generated. I'm not hiding any code. What you've seen in the notebook is the only code that's written. We can see the pipelines that we showed before. We can see a preview of the production data, statistical analysis of every feature. Those statistical analysis of the features is actually used by the model monitoring to detect drift. How do we know what's an anomaly? We have to analyze the data. So on one end, the feature store is analyzing the data, and then the model monitoring using that analysis to compare it with real-time data. So we can go into the models. We can see the models that we've built, all sorts of metrics of those models, the features, and the schema of that model, etc. We can see the different endpoints that it is running, currently 1. And we can see analysis of the drift and the features. There's also a very nice Grafana dashboard. You can see that in the documentation that's built on the same data. Is a lot more interactive than what you see here in the user interface. So, so with that, this is, again, there's lots of things to show. I'm not going to show everything in one short session, but you can learn a lot about MLRun. Again, there are Katacoda learning sessions. There's lots of data in the documentation. There are demos. We're going to release those Colab examples that you've seen, just one click, and you can run off of it. We're doing a huge effort on in the community. There are many contributors from different companies who contribute to that project. Help us, join us. If you like it, add a star in GitHub. And so with that, I'm going to go into the set of questions. Okay, but by the way, there are people asking about the code. All the code is also maybe not exactly the last version, but you can find it in the MLRun documentation. They go to the different getting started tutorials or different tutorials, and you'll see that. Again, another place is the MLRun demos with more comprehensive examples, deep learning, NLP, time series, and so on. By the way, we're working now, me and another colleague, on writing a book that covers all those different cases in a lot more details. So stay tuned on that. I can potentially share the links here. So I'll share the links in the chat so people can just go and see. And by the way, if someone finds something in the documentation you want to change, edit, you can open issues directly from here. If it's a notebook, you can download and run it directly from the documentation. Okay, let's try and put the other questions. The slides will be available, so I'm going to make them available. And everyone that wants additional data, you can send me information through LinkedIn. You'll find me on LinkedIn. You can connect with me and ask the questions. I'm more than happy to help on that. I see a question on GPU. So there is actually one of the demos here that's focused on GPU. There are actually 2, the NLP and the mask detection. And you can see here how you automatically, these pipelines include the optimizations with Onyx, etc. It also shows how to work with GPU, without GPU, by just changing a configuration parameter, number of GPUs, number of containers you want to distribute your workload on. You can see that in this mask detection example. It also has a real-time pipeline for image processing. And also there's a cool functionality for Onyx compression, which does very nice performance boosting, about at least 10x performance boosting by compressing the model. Yeah, so there's this question in here about the quick start. We're working out to, there's going to be a new version of the different tutorials. We got some feedback because there's also some student classes that work with the material, and we're going to do some changes on that soon. So I'm using essentially some of the new versions that are still not committed. So there is a question, how do we do serverless serving when you require GPU usage? So MLRun uses the underlying engine under MLRun for serving is called Nucleo. Nucleo is another open source project of ours, very popular. It's about, I think, more than 4,000 stars in GitHub already. And it's much better than like Amazon Lambda, is relatively slow. Nucleo has a real-time processing engine and is stateful. It knows how to manage states, and it has dynamic allocation of resources, including GPUs. Has a lot of optimization specifically for CUDA libraries. 4.4 thousand stars already. So MLRun is using Nucleo as the real-time processing engine for the serverless functions. It's essentially creating those distributed pipelines on top of the Nucleo engine. So, there is a question here on online feature store. I'm not going to be able to explain it in a short time, but in general, think of it, those Nucleo serverless engines, you can essentially distribute them, multiple of them as a pipeline. You can choose how the processing is distributed across horizontally and vertically, and they're connected using streaming protocols, Kafka or other streaming protocols. And essentially, you build classes, and those classes are distributed across those serverless functions. They do the processing. There are many data operations like aggregates and joins and stateful computation. Just like you've seen, the only thing I added was add aggregation. I didn't need to specify how to do the windowing, etc. This is automatically built using the built-in aggregate function. There are built-in functions for working with different sources and different targets. Like you want to query BigQuery, run a set of transformations, and write the results. So again, all those things are built in. The feature store supports 3 different engines. One is using the serverless engine using Nucleo. This is more for like stream processing, real-time workloads. It supports Spark engine. So MLRun also has distributed Spark built into it and distributed Dask, so you can create feature store objects and transformations, then deploy them over Spark or Dask or Nucleo. And again, but ping me, we can point you. There is also lots of data in the documentation on the feature store, and specifically on the ingestion flow and so on. So you can go and go over that. There's architecture. If you're interested about the model monitoring, there's also lots of information on the model monitoring and how it's essentially architected. Again, and if you really want, it's open source. You can just dive into the code and look into how it's working. There is a question about third-party validation. Needs can be taken care of. Yeah, so there are many third-party integrations, including validation tools. One of the nice examples, for example, is working with Azure ML. So essentially, we can create a snapshot of data going into Azure ML API, doing AutoML, grabbing back the modes, putting it in as a plug into a real-time serving pipeline. So there are many different integrations. Some of the integrations are through built-in classes. Some of them are using the function marketplace that allows us to build functions for integration with different external services. And you can do the same, build add functions or classes into it. So there is a question, what does Iguazio provide on top of MLRun? So Iguazio provides a fully managed service. So MLRun is an open source, but then you need to install it over Kubernetes. You need to integrate it with security and identity management and RBAC systems, API gateways, storage, and monitoring and metering. When you go into Iguazio, it's all fully managed. You log in, you work, and that's it. In this Colab environment that I showed you, I'm essentially working against the Iguazio cluster. The only thing I need to do is just put the credentials as environment variables or environment variable file, and I just work against the service. I don't need to do anything special. Iguazio also supports on-premises, not just in the cloud, and support all the different clouds. So that's the advantage of a managed service. Okay. So regarding the third-party validation, if you have more details, so ping me and so we can talk about more specifically. Okay, so thanks everyone for asking questions and being engaged. And again, if you want more information, just ping me over in LinkedIn, and I'll try to do my best to answer.